I want to look at the aerodynamic force relationship to pressure and viscous stresses a little more carefully. In particular, I want to focus on the pressure force, and we'll look at an example of the net pressure force on a wing. The reason for doing this is that the lift generated by a wing is really directly related, dominated by the pressure force on the wing. So we have sort of two purposes for this video. One is just getting more familiar with the integration of pressure in particular and viscous stresses on a wing. And then the other is just to start understanding a little more about the generation of lift. With that, the net pressure force on a wing, we'll take a look here at a wing from a planform view. So X is the body axis in the X direction, which roughly aligns with the streamwise direction, and Y is the spanwise direction, and so Z is coming out of the screen here. And if we look down upon the wing then, from the positive Z direction, that's called the planform view. And I'll just also note here that the surface area, when you view it from the planform view, is called S-planform. Right, so there's an upper and lower surface here. We're not accounting for both sides. This is just look down on the wing from the positive Z direction, and the area that you would see is called the planform area, and we'll label it S-planform, like we have here. Okay, and then I can take a cut through that wing, and that'll produce a airfoil cross-section when I cut through the wing, and I can view that cross-section in the ZX plane. Okay, so now I'm looking at the cross-section of the airfoil, of the wing, called an airfoil. And one length I'm going to define here is the chord length. The chord length then is we can think of it as sort of being analogous to the planform view, but now we're talking about the two-dimensional cross-section through the airfoil. So if I think of viewing the airfoil from the positive Z direction, I'll see its length as the chord, as what's defined as the chord. And because the wing generally will have a chord which will vary as you move along the span, right? So as I move in the Y direction, the chord varies. We think of the chord then as being a function of the spanwise location. C is a function of Y, the spanwise location. Okay, so we've just defined two important quantities: the planform area, which is the area viewed from the Z direction, the area of the wing in this case, and then the chord, which is the length of the airfoil, again viewed from the Z direction, and that C is a function of Y for a typical wing. Okay, now the aerodynamic force relationship that we've discussed in the notes is that the force due to the aerodynamics is the integral of the pressure force, which is minus P n hat, plus the viscous stress contribution, which we just label as the tau vector, the viscous stress at some point on the wing. Integrate that over the entire body. That gives us the aerodynamic force. And I'm going to break that into two contributions, the pressure, and label the pressure force AP, and the viscous force A tau. In the notes we use a boldface notation for vector quantities. We'll use arrow over the top because in the notes I can't write in boldface very easily. So a vector is got a vector on the top for my notes, and in the actual notes on the screen you'll see a boldface. The hat notation is to say that it's a unit vector, so n is a unit length vector. Okay, so a tau is then just going to be the integral of the viscous contribution. Let's suppose we want to look at the viscous stress, the net viscous stress in the Z direction. So I'm going to look at the Z component of a tau, which I can just find by dotting it with the Z unit normal, which we define the Z unit normal, we usually use the notation as k hat. So k hat is just the unit vector in the Z direction. So if I take the dot product of a tau with k, that gets me the Z component of the viscous stress. Okay, and I can do that by just substituting in by multiplying by k hat, and I can see then the viscous stress net force in the z direction is the integral over the body of tau dot k ds. Okay, and I could define the same thing for the viscous stress in the x or the y direction, and I'd get the similar kind of result here. What we're going to pay attention to, though, is the that look at more details, the pressure force in the z direction. Okay, so AZP. And just like with the viscous stress, that's just taking the pressure force and dotting it with K. And let's do that. So I've got the pressure force, and now I'm dotting it into the K direction. So I've got minus P n hat dot K hat ds. Okay, and that would give me the Z component of the pressure force. Okay. Now I can do a little more work, but what I want to do then to do that is I want to interpret this result, this piece of this here. What's n hat dot k hat ds actually mean? Okay, to do that, let's look back at the pictures we've been drawn, and what we'll see is that we can interpret this as the surface area for that small little surface element ds viewed from the positive z direction. So here's my airfoil, and I've picked a spot here towards the leading edge of the airfoil, and viewed in the cross section, the normal at that location I've drawn in green here. Now, of course, viewed from the planform, if I go over to the planform location here, the normal will have a component which will be along the leading edge viewed from the planform. So this is one view of the normal, this is another view of the normal in that location. And ds then is going to be the surface area, and again I'm just viewing this kind of in the 2D cross section, but there's a small patch here in the planform view also, or there would be. So now if I look at what does ds n hat dot k hat mean, well, the k hat direction is in this positive z direction, so I can draw two lines in here, and n hat dot k hat would just give me, times ds, would just give me this surface area viewed from up above. Right, so n hat dot k hat ds is the surface area viewed from the positive z direction. It's greater than 0 for the upper surface, because n hat then will be in the k, oriented roughly in the k hat direction. And then if I look at the from below, because n hat will be pointed generally downwards in the negative k direction, then from below the lower surface will have a negative value. Okay, but the positive negative value is really just a matter of which general direction k hat has relative to n hat. Okay, and the other thing to note would be that if I were to say look from the leading edge direction in a where somewhere where the vector is largely pointed into the x direction, so there's no z component, then in fact, though there's surface area there, I don't see the surface area when I view it from up above. So around the leading edge, n hat dot k hat can actually be 0. Here with the spanwise, with the leading edge having this shape, it probably won't quite happen that way, but that's the general idea, is n hat dot k hat could also be 0. Okay, so let's look at this a little more carefully then. I'm going to take this integral and I'm going to break it into an upper surface integral. So S body will be an integral over the upper surface and then an integral over the lower surface, which I just add together. So from the upper surface, I can call the pressure P, I'm going to label that with a subscript U to denote that's the pressure on the upper surface. And I'm going to replace n hat dot k hat ds with what I'm going to call ds of xy, which is the surface area viewed from the z direction, which would be surface area in the planform axis, so xy appears here. Right, okay, so this integral here for the piece that's on the upper surface is minus the integral of the upper surface pressure times ds xy, which is the planform area on the upper surface. And I get the same thing except for a minus sign for the lower surface, which is PL ds xy. But you can see I don't, here I've got a plus, here I've got a minus. The reason for the plus here is that n hat dk hat dotted with k hat is a negative value, like I mentioned here. So that flips the sign of this integral. Okay, so the last bit of this is to recognize, well, okay, this is just an integral over my planform area. So I can get to my final result here, which is the pressure force in the z direction is PL minus PU integrated over the planform. Okay, now I just want to spend the last minute or so just thinking about what all that means. So rewriting the result that we just derived here, that AZP is the pressure difference PL minus PU integrated over the planform. One thing to note is that in many cases of interest, the lift direction is about in the z direction, right? The angle of attack tends to be small, so the streamwise direction is in the x direction, and therefore the z direction will be aligned approximately in the lift direction. So while I'm talking about AZP here, in fact, the lift is going to be very much dominated by this quantity. The other aspect of this is that the viscous forces in general tend to be small in the z direction. Okay, so that leads to the conclusion here. AZ, the magnitude of AZ tau, the viscous stresses in the z direction, is much smaller than the pressure forces in the z direction typically. So the result here is that the lift is approximately equal to AZP in many practical cases. So this result about how the pressure difference is related to AZP also is just telling us that the lift is going to be related to this pressure difference integral. Okay, now we can go one step further and define an average pressure difference where this average pressure is 1 over the planform area times the pressure difference integrated over that planform area. So I can think of AZP as being equal to the average pressure difference between the lower and upper surface multiplied by the planform area. Okay. So because the lift is very much dominated by AZP, then I can say the lift is approximately equal to the average pressure difference between the upper and lower surface multiplied by the planform area. Okay. And this will be important because this tells us now that if, say, we had a wing that kept its general shape the same, but we just increased the planform area, then we would expect the lift to scale with whatever that increase in planform area is. Or if I kept the planform area of the wing the same but wanted to increase the lift, I'm going to need to figure out some way to increase the average pressure difference between the upper and lower surface. And this will become important here throughout the rest of the class. We're going to use this kind of result. And in a second, we're going to actually define a lift coefficient which uses this result that the average pressure multiplied by the planform area is related to the lift.